Let's look now at a point of interest that is off to the side of the endpoint of a current carrying wire here. So let's set up for this case here. I'm going to make a couple adjustments to what I have on the screen. I know this distance here is given as r, but I want to draw in my coordinate system a little more neatly. So I'm going to go ahead and do that. So I am going to put my y-axis in right here. And then I'll say the axis that the wire is on is my x-axis there. Okay. In this case, I'm going to have positive x be off to the left. I'll have positive y be upward. And then this, of course, here is given as big R. And I'm going to set up that way. I'm going to set up with my origin right here. So this point here is x equals 0, just to be clear, with positive x off to the left now. So yeah, I'll draw in my current element and we can kind of go from there. That's our setup. So if I draw in my little current element here, ds, and that has some length, dx. I'm using x-axis, so I'm going to use x there. I can draw in my r vector. R is always going from the current source to our point of interest. So r is vector, sits right here, and my angle phi is going to sit in here. So what's phi, right? That's, well, when we draw or when we express our magnitude of dB in Biot-Savart, we write the vector expression out magnitude-wise. We get mu naught I over 4 pi, and then we write this cross product out in magnitude, and we do that. It's the magnitude of the first vector multiplied by the magnitude of the second vector and multiplied by the sine of the angle between them. Okay. So that allows me to go into magnitude, and that's what I integrate. Direction we get from right-hand rule. We don't get direction from doing any kind of calculation here. We get that from physical analysis, and we can pause for a moment and do that now, actually. And if I look at my point of interest, which is P2 up here, and I consider my right-hand rule that the direction of ds is in the direction of current, so that's left to right. And that's going to be crossed into R, which is kind of going up to the right there. So I do that ds cross R right-hand rule. That gives me a dB that is coming out of the page. Okay, that should be pretty clear. Work on that. Talk to me. Spend some time on that if that's not clear. That right-hand rule analysis piece should be a piece that you're pretty comfortable with at this point. So all right, we can go, I think, start expressing stuff here now. We know that my r, I can do this over here, my r, I can write as the square root of x squared plus big R squared. So big R is if I'm looking at my my right triangle here, of which little r is the hypotenuse. Remember what x is. X locates our current element, our differential element, with respect to the origin. So x is actually right here. It goes from the origin to our differential element. So it's the base of the triangle, conveniently, for this problem. And that informs my coordinate system choice, right? Is like, what's a way that I'm going to be able to fairly conveniently express r. Another thing that I can express then is my sine phi. So go ahead and have a look at that in your right triangle there, right? That sine phi is just going to be big R over little r there. So what that means is that my dB simplifies kind of nicely. My dB mu naught I over 4 pi. Let's see, big R dx over x squared plus big R squared all to the 3/2 power. So that's just making those substitutions, making that substitution for sine phi, right? There's my sine phi, and making the substitutions for R here And here's what I have for R. Okay. So once I've made those substitutions, then I have my expression for dB, and then I need to integrate that. So I know that if I'm going to find my B, I have to add up all the little dBs due to every little segment of this wire. This is fairly straightforward as far as contributions from each particular segment. The dBs are all going to be in the same direction. They're going to differ in magnitude, of course, because my R has a different magnitude as I move around on the wire. So I can pull out my constant stuff, so that'll be mu naught I and R and 4 pi. And then I can integrate my dx over x squared plus big R squared to the 3/2. And then I want to look here at my bounds, and they're going to go from x equals 0 to x equals L. Yeah. So I would integrate this using the table or some method of integration. And then I would evaluate it from 0 to L. And I'll leave that to you to work on there. What I end up with for my B at 0.2, so I can call that B sub 2 or something, that will be equal to mu naught I over 4 pi R times L over root L squared plus R squared. And that is all coming out of the page. So notice that, like, if you have a case of, say, a semi-infinite wire, that's what it's called. If you're on the end of a wire, but the wire is infinite off in the other direction, then you would simply just change your bounds, right? From 0 to infinity there. So there are a lot of ways that you can deal with a lot of different straight wire cases. You'll notice a lot of similarities, and you can handle the differences simply in the bounds of integration.